Hi, my name is James Walker, and I'm going to talk to you about my work with combined remote sensing methods for active charge control using an electron beam in a dynamic space environment. When exposed to the energetic plasma of space, spacecraft are going to charge. The energetic electrons, protons, and photons are going to impact the conducting surface of the spacecraft and cause it to generate currents on it. When these currents balance, we're going to have a relatively stable floating potential maintained on the target. Now, the actual value the target charges to is going to depend on the region of space that it's orbiting in. Um, in GEO, where this work is mainly applicable, spacecraft potentials can range between tens of kilovolts negative in eclipsed regions to weakly positive, so 10 to 100 volts positive in sunlit conditions. And these floating potentials are caused by the current balance between all the environmental currents that the spacecraft experiences. However, spacecraft can actually be equipped with energetic particle beams, such as electrons and ion beams, to apply additional non-environmental currents and manipulate its own potential. Now, this has actually been explored for decades now. There's been a lot of work done in active charge control, um, including in situ missions. So some of the first in situ missions were ATS 5 and 6, but then that work also evolved into the development of instruments that allow spacecraft to relatively accurately control their own potential in positive sunlit regions. And instruments like these have been employed on missions such as Cluster, Double Star, MMS, to name a few, and they've been used relatively extensively. Uh, However, in each of these cases, the spacecraft is controlling its own potential. So through ion emission, the spacecraft is able to lower its potential from a positive value to a near zero value. Um, And the work that I am focusing on is actually controlling the electrostatic potential of a target object. So instead of controlling a potential of yourself, you're controlling that of an uncontrolled object. And this can be really beneficial because if you can control the potential on each of the two objects, you can control the electrostatic force generated between them. And this would be beneficial for proximity operations, decreasing the likelihood of arcing during docking in these high potential regions. But the main motivation for this work is the electrostatic tractor. So the electrostatic tractor is a novel method for debris removal that utilizes spacecraft charging. The idea is you have a servicer equipped with a high energy electron gun, irradiating a target with negative electrons. This increased negative current is going to cause the target to charge negative, while the emission of the negative particles causes the servicer to charge positive. These opposing charges generate an attractive Coulomb force between the two objects, which allows the servicer to actually tug the debris object to a graveyard orbit. And it was found that by maintaining tens of kilovolt level potentials, positive and minus on the servicer and the target, and maintaining a separation distance of about 10 to 15 meters, a multi-ton debris object can be reorbited in a matter of months. However, in order to employ this technique, we have to be able to control the electrostatic potential of both of the target and the servicer in order to control the electrostatic force generated between them. And we just showed that it is possible to control the electrostatic potential of the servicer that has seen a relatively extensive body of work, but there hasn't been much work looking into controlling the potential of the target. So some prior work that we've conducted in our lab was to actually investigate this, looking at controlling the electrostatic potential of a target. And we found that by using a feedback controller on the energy of the electron gun, we can actually achieve relatively stable control of the target's potential. So for these this paper and these experiments looked at charging in an idealized environment, so only considering electron beam induced currents in a vacuum chamber environment. But what we found is that through both numerical analysis and experimental analysis, we were able to achieve uh, stable control across a variety of initial conditions. And we were also able to match our numerical and experiment results fairly well. Now, this was conducted in an idealized environment, and we used special equipment to get quick and accurate measurements of the target's potential, neither of which are realistic for an in situ application. So the next step of this work is to start removing these idealized assumptions and making it into a more realistic scenario. And one way we do that is we want to integrate active charge control with remote sensing methods. So our lab at CU has actually developed two methods for remotely sensing a target's electrostatic potential. The first is the X-ray method. The idea is you have a surfacer irradiating the target with electrons. As the electrons interact with the target surface, X-ray photons are going to be emitted from the target. And by measuring the energy of these photons, specifically the maximum energy of the emitted photons, we can then determine the potential of the target. And when integrated into our active charge control, we are able to still see we get this nice stable control. But there is one issue. So the X-ray method depends very strongly on the secondary electron method. The accuracy of the X-ray method depends significantly on the accuracy of our measurement for the noise floor. So we have to have an accurate measurement for the background X-ray radiation that is experienced. And what we found is that for our experiments in our vacuum chamber, if our minimum photon level, if our noise floor is off by 5 photons, we can get a difference in the measured potential of 300 volts. And the concern is that when we move to a more variable environment such as that of a realistic space environment, we're going to see that this variability in the noise floor is going to have an even more significant effect on the measured target potential. And the outcome of this in terms of our charge control is that we get a lot more inaccurate measurements, we get a lot more noise in the control, and ultimately we don't get a nice stable convergence down to our goal potential. We actually get a lot of oscillations and wiggles around that final goal potential. And interestingly enough, the amount of variation we get in the final convergence is also going to depend on our initial conditions, such as when we want to converge down to 1 kV, we get this nice stable convergence, but moving it down to negative 2 kV, we get a lot more of this noise. So it's inconsistent between each trial as well. The second method we looked at was the secondary electron method, and it is similar to the X-ray method where we use electron beam to irradiating a target object. This is now going to generate secondary electrons, which are repelled away from the negative target towards the positive surfacer. And again, measuring the energy of these electrons, we can determine the potential of the target. To do this, we use an RPA, a retarding potential analyzer, which acts like a gridded Faraday cup. So on the external grid, we have it grounded, and the internal grid, we perform a voltage sweep. So we gradually increase the potential of the internal grid and measure the current of the electrons flowing, being measured by the equipment. As the potential of the internal grid increases, once the potential of the grid is greater than the energy of the electrons will not be able to penetrate the electric field and be repelled away. And this will correspond to a steep drop-off in measured current. By determining where the steep drop-off is, we can determine the energy of the particles. Again, when integrated into our active charge control, we get that stable control. But now we have different concerns that arise. The main being that the secondary electron method depends significantly on the voltage sweep being conducted. So in order to scan every possible energy that the spacecraft can be in, we have to perform a very wide voltage sweep. For instance, if in GEO, the potentials range from 0 to 10,000 volts. In order to measure any possible target potential, we have to have a voltage sweep from 0 to 10,000 volts. And this leads to very inefficient and slow control. The main reason being, in order to perform the secondary electron method, we only need to determine where that steep drop-off in current is. So we really only need a couple measurements above and below the target potential, indicated by this purple region here. So any other measurements, any other values found for the voltage sweep don't actually factor into the calculation of the target potential. So performing that huge massive voltage sweep is very inefficient because it doesn't play into the measurements. So we have these two methods, each with their positives and drawbacks. The idea is, can we combine these two methods to leverage only the benefits of them? And that leads to the dual method. So the idea of the dual method is to seed the secondary electron method with an initial X-ray measurement. So the issue with the X-ray method is it's not incredibly accurate. We can, with a decent calibration of our equipment, get the measurement to reliably fall within 200 to 300 volts for the scenarios that we've tested. So the idea is we get this accurate measurement, this accurate estimation from the X-ray method. We know the target potential is within 300 volts of that. So we feed that into the voltage sweep of the secondary electron method and do a sweep around the estimation plus or minus 300 volts. So instead of having 0 to 10,000 voltage sweep, we have a voltage sweep that is about 600 volts wide. And this ensures that we're only getting values above and below that target potential. We're not getting all the extra extraneous stuff. And this leads to much faster and more efficient control, while also giving us the accuracy that we get from the secondary electron method, the accuracy and consistency in the measurements. This work is mainly experimental, and experiments are conducted in the Eclipse vacuum chamber at CU. This vacuum chamber was specifically designed to explore charging behavior of spacecraft. So getting right into it, once we integrated our dual method into our active charge control, we found that we are able to still get that nice stable control. And interestingly, one thing that we find from our trials is that the X-ray method consistently underestimates the actual potential. And this actually makes sense with what we would expect. This refers to how the noise floor affects inaccurate measurement in the noise floor affects the actually computing the X-ray method. We would only ever expect it to underestimate the actual potential. It would be very rare for it to overestimate. And we can actually use this to inform our voltage sweep. So instead of performing a symmetric voltage sweep, we can actually skew it to account for the fact that we're likely underestimating the potential with the X-ray method, leading to even more efficient control. What we also find performing a gain analysis, we see that we get a gain of 1, the control converges in a single time step. And this is what we would expect based on how the secondary electrons and backscatter electrons affect charging, and is consistent with the other gain analyses that we performed, both in the numerical analysis as well as other remote sensing methods being integrated. So we do get the consistent behavior we would expect as well. Comparing our dual method to our previous other implementations of remote sensing, we can see that we do get faster and more efficient control with the dual method relative to the secondary electron method. And in fact, this plot is even a little misleading. For the secondary electron method, we swept from 0 to 5,000 volts with a step size of 50. For the dual method, we did a voltage sweep with a step size of 20. So to actually have the same level of accuracy between these two plots, the secondary electron method, so the blue line, would actually be expected to take 2.5 times longer. So instead of a measurement every 250 seconds, we would expect a single measurement to take over 600 seconds. So we see that the dual method is significantly more efficient than just using the secondary electron method. We also see we get more consistency in the final convergence than we do with the X-ray method. So the measurements of the dual method are more accurate just in general, but that once we get down to the actual converging to the negative 2000 volts, we get a much more stable behavior around that goal potential with the dual method compared to the X-ray method. So we are able to successfully leverage both the benefits of our two prior methods in the dual method by combining them. But we've only evaluated these remote sensing and the active charge control in an idealized environment, so a vacuum chamber with a target only irradiated by an electron gun. And we want to expand this again to more realistic scenarios, so we're actually going to include an environmental current. In this case, we're going to use a vacuum ultraviolet light, so a high energy photons, to apply a positive photoelectron current to the target. And this is representative of a spacecraft coming out of eclipse into sunlight. So we're going to be we're going to be turning on the UV light and applying this current while the spacecraft has already begun charging, simulating coming from that very negative environment of eclipse to the weakly positive environment of sunlit regions where the dominating solar photon currents is applied to the target. So taking a step out of experiments and looking at stability analysis, the full stability analysis presented in the paper, but just looking at the highlights here, we can see that we have the same charging equation as we had with the original active charge control, but now we have this additional IPH term, this additional positive photoelectron current. So performing the same stability analysis, we take our differential equation and we linearize it around the equilibrium state, the goal state of the system. And what we see is that this IPH term actually falls away. It does not appear in our linearized equations. And this occurs because in order to perform this linearization, we take the partials of our initial state equation with respect to our state variables, the target potential and the electron beam energy. And the photoelectron current doesn't depend on either of these variables. In fact, for a negatively charged object, the photoelectron current is constant with respect to our state variables. So what this means is when we take the partials, it drops away. And it drops away. And then when we continue the rest of our stability analysis, that term doesn't factor in. And we end up with a gain condition that the proportional gain of the feedback controller has to be between 0 and 2. This is the same condition that we found in the idealized environment. So what this tells us is that a constant positive current will not affect the stability constraints of the system. And this is actually a very interesting result because the solar photon current that spacecraft experiences is one of the most dominating currents that it'll experience throughout an orbit. So this suggests that our control is robust to one of the most significant environmental currents a spacecraft will experience. Going back to experiments now, we want to look at the relationship between measured potential and beam energy. So the stable potential that each beam energy achieves on the target. So first, looking at without the VUV lamp on, we see this nice linear relationship. This is what we would expect and what we see in all of our previous results. We also see that the current of the electron gun doesn't factor into the floating potentials, which again is what we would expect. But now once we turn on the VUV lamp, this changes. In fact, with a beam current of 5 microamps, we see that the target doesn't actually charge. And this does expose one of the assumptions that we make in our stability analysis, and that is that the target charges negative. If the target charge is positive, then we do have a dependence on the state variables because the photoelectron current is going to depend on the target's potential. And additionally, one step further than that is the target actually won't ever charge negative if the photoelectron current is greater than that. Our equation on the top, our state equation, if IPH is greater than the ion beam current, that value is always going to be positive Therefore, we can only charge the target positively. We can't decrease its potential. So what this actually tells us is in order for our control to still hold, our electron beam current has to be greater than whatever constant positive bias the spacecraft is experiencing. And we see that once we increase the current to 13 microamps, we get charging occurs at about 5,000 volts, and then once it occurs, we get that nice linear relationship that we would expect. So exploring our remote sensing methods and our active charge control in this dynamic environment, we see that when we have the VUV lamps off, we get the normal charging that we expect. And then once we turn the VUV lamps on, the target jumps up to near 0 because we now have this positive current that's dominating the charging behavior. And we're able to still accurately measure the target's potential and increase the beam energy until we start getting charging again. So we increase the beam energy. The electron beam current is now greater than the photoelectron current, and we are able to get this nice control again. So we are able to, our feedback controller is able to function in this dynamic environment with this constant positive bias. But additionally, what we would expect is that the behavior doesn't depend on the current bias actually being positive, because if we have a constant current, it's not going to depend on the state variables, and in that term is going to drop away in our linearization. So at least around our equilibrium potential, we would expect that this controller would be able to handle any constant bias, as long as our electron beam current is greater than that bias. So then finally, looking at comparing all of our remote sensing techniques to a changing environment, we see that we get nice convergence with the dual method. We're able to accurately measure the target's potential throughout the entire trial and across all tested trials that we looked at. But now when we look at the secondary electron method and when that's employed, it appears initially that we get similar behavior. We're able to measure the target's potential accurately, albeit slower, and get this nice convergence. But this will not always be the case. So here we are measuring between 0 and 4,000 volts for our voltage sweep, and turning on the VUV lamps makes the potential jump from negative 1,500 to 0. All these values are within the voltage range. But say instead we had a negative current bias, which actually caused our target potential to jump to negative 5,000 volts. Now, in this dynamic environment, because our voltage sweep is only from 0 to 4,000, we're not accurately measuring the target's potential anymore. So even though it appears for this positive bias, we are able to get nice control. If we were to have a negative bias or just in a dynamic environment, the potential jumps outside our initialized voltage sweep bounds, we won't be able to accurately measure or control the target's potential anymore. And then finally, looking at the X-ray method, we again see this nice control. And actually, again, what we initially see is that we get very stable behavior around our goal potential. We don't get a lot of oscillations. We get this very nice convergence. And this initially suggests like, oh, if we're able to get the accuracy with the X-ray method, why would we need the dual method? But it actually reveals a bigger issue with the X-ray method. So the reason this is stable is because the minimum photon count, the noise floor, when the VV lamp is on, is about 100 photons. It changes slightly between trials, but it's relatively consistent. And if we think back to our previous slide where we were looking at the noise floor, without the VV lamp, just the electron beam, the noise floor was about 10 to 15 volts. So across this dynamic environment, the noise floor jumped from 10 volts to 100 volts, a whole order of magnitude. And this is still in a relatively idealized scenario, vacuum chamber environment, and a lot of variables we control. So we would expect that in an actual space environment, this noise floor could be very variable throughout the entire orbit. And unless we have like a very good model for how the background X-rays would evolve throughout the orbit, we're going to get really inaccurate results for the X-ray method across an entire dynamic environment. So actually, we would expect the X-ray method to perform far worse in a more realistic scenario. So we still have some significant concerns with the second electron method and X-ray method, but we'd still have the robustness with the dual method in this dynamic environment. So the conclusions that we can draw from this work is that we are able to integrate the dual method into our active charge control, and we are able to leverage the benefits of both the second electron method and the X-ray method using this technique. And this will allow for quicker and more accurate charge control of the target object. We also found that our feedback controller for our charge control of the target is robust to constant current biases as long as the electron beam current we are using is greater than that of the bias that we're experiencing. And then finally, that the dual method is relatively robust to a changing environment and can measure an entire full environmental space, as opposed to our second electron and our X-ray method, which are not as robust to this changing environment. This work was funded by the DoD through the NDSEC Fellowship, and as well as general electrostatic tractor research has been made possible through support from AFOSR. So with that, thank you for your time. If you have any questions, feel free to reach out.